Hi, everyone. Welcome back. We're going to get started with the afternoon session today. And for our first talk, we have Inbal, Livni, Navon from Stanford telling us about a new decoding algorithm for hypergraph product codes.
So hello, everyone. I'm Inbal. I'm a postdoc at Stanford, and I'm going to talk about Viderman's algorithm for the hypergraph product code. This is a joint work with Annie and Mary that are both here. So I'm going to start by what's going to be in a talk. I'm going to start by some background, and then I'm going to talk about decoding the classical LDPC code, and I'm going to talk about hypergraph product code and to show our algorithm, to give some high level for the proof of the algorithm, and going to finish by some summary and open questions. So I suppose I don't really need to motivate quantum error correction code, but we want to correct errors in quantum computations. And one way that seems like a good way to do it is using LDPC codes because they're very local. So today I'm going to show a new decoding algorithm for the hypergraph product code. And so I'm going to start by classical LDPC codes. So we have a code, NKD encodes k bits with distance d. And the parity checks graph is sparse. So we have this bipartite graph. It has degree delta v delta c that are both constant. And a word is in the code if all the parity checks, which are described by the graph, are 0. So here I don't have an inner code. I require all the parity checks to be 0, and this is during the entire talk. So this is the classical LDPC code. In the quantum case, we have the same. We only use qubits. It's created from 2 classical codes. And again, each vertex here has a constant degree. And so in the talk, I'm only going to talk about correcting z-type errors and what we assume that these errors are reduced. So if, for example, we have this error, and then we can flip this neighborhood of this vertex, and then we get an error that has a lower weight. So this is the error that we're going to consider. OK, so now, in order to do both classical and quantum decoding, we need a graph to be an expander, specifically vertex expander. So what do I mean by an expander? A bipartite graph is alpha epsilon expander if for any set of vertices S in the V side, it has many neighbors. And when I say many neighbors, I mean nearly the maximal number of neighbors it can have. So for example, if we have this set S, and we have degree, which is delta V, then we want a set of neighbors of S, which I'm going to denote by lambda of S, to be nearly delta V times S. So nearly the maximal possible, where epsilon during the talk is going to be some small constant. You can think about it as like 1/20 or something. So this is what we need from the graph. And random graphs satisfy it, but also there are explicit constructions that satisfy it. And it is bidirectional if the same also holds from the C direction to the V side. So if we also have a set here, we want it to also expand with nearly the best possible, 1 minus epsilon times the best possible. So if we want to decode a classical LDPC code, there is a very standard algorithm called flip by Cyprian Spilon. And the idea is that you use bit flips to reduce the number of unsatisfied parity checks. So you have some word. It's not a code word. There is some error. And this means that there are some parity checks which are unsatisfied. So what this algorithm does is it checks if you can flip 1 bit, and then to reduce the total number of unsatisfied parity checks. And it continues to do it until all the parity checks are satisfied. And what they showed is that if the error is small enough, then this process works and stops, and you can correct all of the errors. And in this talk, we're going to talk about a version of Viderman's algorithm. So this algorithm does something different. It converts errors to erasures. What it means is it promised to find a superset of the errors. So it finds some set of vertices that is promised to contain all of the errors. And then later on, you can easily correct the errors if you know this superset. So how does this algorithm work? It is very simple, so I'm going to describe it explicitly. So we get some word, which is not a code word, has some noise. But obviously, we don't know which vertices are noise. What we do know is which the set of unsatisfied parity checks exist. So the algorithm starts from this. It has a set of suspicious vertices, which is L, which is the envelope, and a set of suspicious parity checks, which is R, and it's initialized to all the parity checks which are unsatisfied, because clearly they have to touch at least one error. And then it has an iteration. It goes over every vertex. If some vertex is adjacent to too many unsatisfied parity checks, then it declares this vertex being suspicious, it puts it in L, and it automatically puts all its neighbors in R. Because even if this is a satisfied parity check, if it is really adjacent to an error, then it actually must be adjacent to another error. So this is sort of the reason why we want to do it. So then you continue to do this. You look for another bit which is adjacent to too many, now larger set of suspicious parity checks, and you continue doing this process until you cannot do it anymore, so none of the vertices is suspicious. And then you just output your L. And what Viderman showed is that if the initial set of errors is not too large, then you do find a set L, which is promised to contain all of the errors, and to be not too large, where gamma is some constant, you can think about it as like 4 or something of that form. So this is the algorithm. And now we want to use the algorithm for the quantum setting, for the hypergraph product code. So I'm going to start by describing the code. So it's a quantum code. It has linear rate and square root and distance. And it's constructed from 2 expander graphs. And it's actually a product of the expander graph. So I'm going to describe it in a drawing. So we have, this is our original bipartite expander graph. And then the hypergraph product code has each one of its columns, the original expander graph we started with, and each one of its rows, the flipped side of the original expander graph. And now the qubits are all these vertices. So every qubit in our hypergraph product code is V1, V2, where V1 and V2 are 2 of the vertices of our original expander, or C1 and C2, where these are the checks of the original bipartite expander. And X-type parity checks, which is what I'm going to focus on, are indexed by V1 and C2. So then, if we have an X-type parity check of these V1, V2 vertices, this is just all of its neighbors along this line. So it's V1 and all the neighbors of V2 in the original bipartite graph. And if we focus on a parity check and we ask, okay, which qubits is it connected to? These are all the neighbors of this parity check along both the row and the column. So these are the parity checks. Does it make sense? Is it good? Okay. So what's important to notice in this graph is that there are small sets that do not expand. Which are small sets? Are these? So suppose we focus on one of these vertices. And then we look on all its neighbors across the row. So these are these neighbors, C1 and the neighborhood of V2, and its neighbors across on the column. And then we look on all the parity checks which are adjacent to it. So now we have a small set of qubits. These are the qubits. It's a constant size set. But what happens here is that every parity check is adjacent to 2 different qubits in this small set. This is because if you start from C1, V2, you can both go to neighbors of C1 and neighbors of V2, or to neighbor of V2 and neighbor of C1. So you have here every parity check adjacent to exactly 2 qubits. And this means that this set doesn't expand in the definition I defined before as vertex expansion. Instead of having nearly the maximal number of neighbors, it has half of it. This is not a problem in terms of the distance of the code. It would have been if that was a classical error correcting code, but because we only look on reduced errors, the code still has distance. But it is going to cause troubles for the decoding algorithm, which is why I wanted to describe this set. So we want to decode the hypergraph product code, and we want to correct linear fraction of the distance of errors. So there is a generalization of the flip algorithm, which works for the hypergraph product code. And it uses bit flips and sort of like a generalization of the original flip algorithm that reduces the syndrome, the set of unsatisfied parity checks. And we also wanted to do the same for Viderman's style algorithm, so we wanted to do erasure conversion. What does it mean? It means that we wanted to find an envelope L that contained all the errors. So if we have some errors, we wanted to find a superset of the errors, and we wanted it to be not too large, just like the original one, where this should be some constant. So that was our goal, and this is what we did. So we have the hypergraph product code. If the error is not too large, we can find the superset of the error, which is constant size. So it's a different decoding algorithm than previously because it does conversion to erasures. It is a linear time algorithm that finds this set of suspicious errors, and it can handle up to some linear fraction of the distance, where this depends on the parameters of the graph. What is unfortunate, but important to note, is that unlike the classical setting, in the quantum setting, we don't have a linear time correction for erasures. So if we want to actually correct the errors, then the total runtime would be more than linear. So this is unfortunate, but this is the current state. And now I'm going to do a high level of the algorithm. So just like before, we want to find some superset of the errors, but we don't know where it is. And what we start from, just like the standard Viderman's algorithm, is we start by R being the set of unsatisfied parity checks. And then what we have, instead of going over all the qubits, we actually go over some set of small sets of qubits, which I'm going to define this as later on. And for every small set of qubit, we're going to calculate its score. If the score is too low, we're going to do just like the previous Viderman's algorithm. We're going to add it to L. We're going to add its neighbors to R. And we're going to just repeat this process until we cannot do it anymore. And then we stop and output L. So this is very similar in a high level to what Viderman's algorithm is doing. There are only two differences. One of them is we have a collection of small sets instead of going one bit at a time. And the second is that we have a score. So now I'm going to talk about these two things, one after the other, starting with why do we even do small sets? Why can't we do just vertex by vertex? So the classical algorithm, this is what it does. But our problem is we have these non-expanding sets. So what happened here? Suppose we want to check if this specific vertex is an error. And suppose that this is the real error pattern. All these orange vertices are the real error, and this is the entire error we have. So this is a reduced error because it's less of this entire local view. And this would be the set of unsatisfied parity checks, which are all the parity checks adjacent to only one error. So what happens here is that if we want to add this vertex, we have to set our threshold h to half. Else, this vertex would not seem to be suspicious. But if we set it to half, this is very low. We will not be able to bound L. So what might happen is that our set L is going to grow, and we might return something which just contains the entire set of qubits and is meaningless. So sort of this doesn't work. So we need to go and look for small sets. And these small sets are going to be exactly the small sets that are problematic. So we're going to look on all reduced sets in all local views. So every set which is half, at most half of the qubits in a local view, is the collection of sets we're going to look at. And what's important to notice is, first of all, it's a linear number of sets. This is because we have a linear number of local views. Yes. So these are what I described at first, that you start from a z vertex and you look on all its neighbors, and then you look on all its neighbors along both the row and column. So these are its neighbors. And these are the subsets of all of these neighbors is what we're going to look on. So because you have a linear number of these z-types, parity checks, and each of them has a constant many neighbors because it's a constant degree graph, and these are the sets that you're actually checking.
So you check all subsets?
All subsets of this form of sets of vertices, yes. So we can do it in linear time because it's a linear number of subsets. And this is a more intuitive claim that they are covering all these non-expanding sets. So sort of it's enough to look on these sets of small subsets to handle this annoying situation where you have a non-expanding set. And then the second part is, okay, now instead of a vertex, we have a set. And then how do we say if a set is suspicious? It is not as straightforward as a vertex because you also have a structure of the set. And for that, we have a score function. We tried a lot of different score functions before we came up with this form. So I'm going to talk a little bit about why we defined it the way it is. The first thing we did was we are only looking on unique neighborhood. And the reason for that is that non-unique neighborhood is in some sense less meaningful. Because if this, for example, was the real error, then the multi-neighborhood, these parity checks that are adjacent to two elements from the set, would have been satisfied. So these give less information, and we do not consider them in our score function. We're also doing intersection with the complement of R and not the R. So these are the non-suspicious parity checks. We can also write a score with complement with R, just going to have a more complicated form. And we normalize by the size of F. And what's not straightforward clear from this format is that this kind of score function takes into account the structure of F, because different Fs, even if they're in the same size, have different sizes of unique neighborhood. Sort of what it means is that these sets that are like more like half-half have smaller unique neighborhood. So they would, if they have interaction with RC, they would like more easily would be suspicious. So in any case, this is a score function that we've used. And now I want to talk a little bit about, yes.
The structure, because you say unique neighborhood, but I don't understand.
Okay. So unique neighborhood are the set of parity checks which are only adjacent to a single vertex in your set. So if this is your set, then the only parity checks we care about for our score functions are like the orange ones. But if your set was, say, all of this size, then you would actually have all of this square as the unique neighborhood, and you would consider all of it. So sort of the fact that we're only considering unique neighborhood, but normalizing by the size of the set, means that we take into account the structure of it.
And what does it mean that you intersect with complement of the set? Because as I understand, you are looking at the set of unsatisfied checks from unique neighborhood.
On the intersection of the unique neighborhood with the actually non-suspicious set. So these are not only unsatisfied, but also...
So your left-hand side object is a set of checks.
Yes.
The right-hand side section is a set of qubits.
Which one?
RC is...
No, RC is so L was the set of suspicious qubits, and R was the set of suspicious checks. So the algorithm like sort of builds two of them together.
And RC also uses unique neighborhood.
So RC is just a collection of checks. It does not have we do not look on its neighborhood.
So
we just have a
all
set of,
checks on the unsighted.
yeah, so these are all checks. This is all checks.
So maybe it would help if you said, like, is large score good or bad? Because it seems like there's some tension. Like, you want RC to be big,
Right.
but you don't want the neighborhood to be big, it seems.
So we want a lot of intersection with RC.
Oh, yeah. Oh, I see. Yeah. So it doesn't matter what the size of the neighborhood so
Yes.
much is. You just want as much
Yeah,
neighborhood.
so if you have a lot of intersection with RC,
So large
then you're
score
thinking
is-
you're not suspicious if you have a large score.
I see.
But if you have very few intersection with RC, what it means is that many of the parity checks that you interact with are suspicious. So you're likely to be suspicious as well. So yes. Okay. So any more questions on the score? Okay, so I'm going to do some comparison with union find. So union find algorithm is for surface codes, which are different than the hypergraph product codes. It does not automatically generalize, but there is a work that generalizes this to the hypergraph product codes, and it does the same in the sense that it also converts errors to erasures. But for the hypergraph product code, it can only correct sublinear number of errors. And the way the algorithm works is very different in the sense that when we do Viderman's algorithm, we're not trying to find an explanation for the unsatisfied parity checks. We're just trying to sort of find a set of qubits we think are suspicious, but we're not trying to actually have them generate these unsatisfied parity checks. So they work in a very different method. So I want to sort of give intuition to why does this seems to work. And the idea here is that every parity check, if it's a neighborhood of an error, it can either be unsatisfied or it can be adjacent to many errors. So because the graph is expanding, many parity checks which are going to actually be unsatisfied, and this is how the algorithm starts. And then it sort of would recognize all these errors that have a lot of unsatisfied parity check adjacent to it. But then what happens is, because it now okay, so all the parity check adjacent to these errors are now also suspicious, it's going to also check and recognize all the other errors. Because it would start from these unsatisfied parity checks, and that would go also for the parity checks that touch multiple errors and are then suspicious. So this is just intuition, and the proof doesn't actually go through this intuition, but I sort of feel like it's helpful to understand what's going on. So how does the proof really work? It has two parts. One of them is to say, okay, it really does cover all of the error. And this starts by assuming we did not cover the error. And then we have a step which is sort of similar to what the small set flip goes. It's you focus on some local view that has a few external interruptions. So it has an error, but its parity checks are not adjacent to other elements in here. And then what we show is that there exists a set that should have a low score, that should have been added during the run of the algorithm. And this is how we conclude that it must cover the error.
But you assume that the error has small enough weight, smaller than the distance.
Right, much smaller. It cannot be up to the distance. It's I'm going to show the parameters later on, but yes. So the second part is to show, okay, we cannot grow too much. And the way it works is, so what we only add a set to L, if you recall the score function, if it has very small unique neighborhood, which is not already in R. And what it sort of means is it cannot have many edges going out of what's already in R. So you only add sets that have few edges going out. But you're expanding. You have to expand because the graph is an expander. So what happens is, because you're expanding and sort of you only add sets that have few vertices going out, at some point you're going to run out of vertices to add. And this is how at some point you're going to run out of vertices to add, and this is how you bound the size of L in an intuitive level. Okay, so now I'm going to talk about the flip algorithm and about the decoding radius we actually get. So the decoding radius depends on this bipartite graph we started with. And I denote by this the degrees, and this is the ratio of degrees. And I assume it's an alpha epsilon expander, so every set of size at most alpha expand with 1 minus epsilon, fraction of outgoing edges. So the first flip algorithm required expansion less than 1.6. And this was the decoding radius, so this is the maximal fraction of error they could correct. And then this is a follow-up work which has better parameters. So it's a more complex expression. What's important to note is that R is delta V over delta C. So R is much better than 1 over delta C. But it has dependence which is more or less proportional to R squared. And we require more expansion. So like sort of the lowest the epsilon, the more you need from the underlying graph. So we need our graph to be like better expander than the flip algorithm, which is unlike the classical setting where Viderman requires less expansion. And we get a decoding radius which is incomparable in a sense to this one, because the more balanced the underlying graph is, the better this expression is. And the more expanding the graph is and unbalanced, then this one does better. So these are uncomparable in terms of decoding radiuses. Are there any questions on parameters? Okay, so, yes. I have, no, sorry. So this is like the maximal number of fraction of error, the maximal number of errors you can decode. So if this is the distance of the code, then theoretically, like combinatorially, maybe you can decode up to half of it, but the algorithm can decode only up to this fraction.
Thank you. Do you think the bound is tight?
No. Both in the two parts, I think, are not tight. Yes.
Did you pick a particular code which satisfies all of these and compare the media?
So, like, did we pick a specific expander?
Yeah, if you pick an expander which they satisfy, it's like less than 1 on 20.
Yeah.
Put all these in.
So it depends also on these degrees. So if we pick, say, with epsilon being 1 over 20, and if this being, say, 1/2, then I think R does better. But if you would pick this ratio as being 3 over 4, then this one would probably do better. It's like a very, it really depends on your degrees and the expansion you have.
So there's no decoding for broad codes that saturates the distance?
No. Also, classically, there is no code that gets really up to the distance. Classically, Viderman gets slightly better than the flip algorithm, but they're both, first of all, they require epsilon being a third, and they're both not really getting to the, but they're getting pretty close. Like classically, I think you get, what's like 3 over 16 or something. Like they get pretty close to half. Say if half is what you can do combinatorially, they would get 3 over 16 or something.
But that's only with the ITCS version.
Yeah, it's a newer version, not the original Viderman's algorithm. But it is true that in the quantum setting, we're much further away from the, like, to reach up to the distance. So summarize, I talked about a linear time erasure conversion algorithm for the hypergraph product. And there are many open questions here. One of them is, can we improve the parameter? As I said, I'm pretty sure this can be improved, both in terms of requiring expansion and in terms of the decoding radius. And also, can we generalize it to codes that have better distance? Because right now, The hypergraph product code is this square root n. There are good codes. Ideally, we would like to decode them as well, but currently we don't know how to do it. And also, can we have a linear time erasure decoding algorithm? Which is interesting because classically erasure decoding is a very simple question, but somehow quantum, it does not work as simpler as that. And this is it. Thank you.
Any questions?
Yeah. So, do you expect this to work with stochastic noise as usual up to a finite fraction?
Like, can we get up to O of n distance with stochastic noise? So we didn't try to analyze stochastic noise at all. I don't know. It seems like if your errors are like sort of separated, it should work. But this is just an intuitive claim. We have not analyzed it at all.
The claim that works well for low amplitude stochastic noise, right? You have isolated.
Yeah. So if you have isolated, yeah. So if we have isolated isolated areas, it should work, but it is not something we analyzed.
Now, how difficult it would be to try for just random hypergraph product code? So because sort of the bigger expansion parameter is suspicious, but then you are saying some other parameters may work in your favor. So really.
So I mean, I don't know how easy it would be to analyze this, because we haven't done it.
So I would say that the actual expansion parameter that we have is in part also a problem with getting our proof to work. I think the actual expansion that we will require in practice might be better. In fact, I would be willing to bet that it's better. And there's parts of the proof that we can also borrow from the fuzzy group and that area from 2018, where when you have random errors, they form these disjoint clusters, as you pointed out. And the envelope that we get, the little L, it expands, right? It covers more than just the error. So it's bigger. And so the question is, the amount by which these blobs are separated, is that enough such that when you have this radius that's more than the size of the error, do they then overlap? Do these two blobs overlap? Because if not, then what you said is right. They're going to be able to correct a constant fraction. If not, so then we're in trouble. So this is exactly what we need to understand. When you have disjoint blobs, and with this algorithm, you have a blow up in the size of the envelope, how far is far enough?
Like, if the graph is very expanding, then we don't get L to be much larger than E. If we go back to the parameters.
Right, but then the cost is if it's very expanding.
Yeah, and then the cost is that it's very expanding.
Small radius of the blob.
Yes. So yeah, if this is say 1/20 or something, and R is not too large, you would get the factor of L being like 10 times the error or something like this. So it's not crazy larger, but it is 10 times larger. So
We're willing to bet that these parameters also we can improve.
yeah, probably they are not tight as well.
Yeah.
Yeah, can you say a bit about how we might generalize this to other codes, like for example these good LDPC codes? Like, what is the difficulty?
So the main difficulty is that the good LDPC codes are Tanner codes, so they have an inner code. And this construction does not have an inner code, and it's unclear how to, because this one only has, suspicious, unsatisfied, and satisfied, and doesn't have this like distance from, like it doesn't have an inner code. So yeah.
So one more.
So I was wondering, even in the classical case for random errors, I don't know that anybody's analyzed this to handle clusters that are separated, right?
So I think in the classical case, people also maybe less consider random errors in this setting. But also you can, in the classical case, you can so here we have this gap of like square root n we can handle, like in like adversarial, and like theoretically, if we could handle this random noise, maybe we can bring it all the way to an n. But the classical autocorrecting code doesn't have, it has a linear distance. So there is less of this huge gap that you might want to consider random errors to handle.
So when you consider the flip algorithm classically, the thresholds you get are tiny, and like almost any other decoder beats them by factors of 10 or 100. So people have looked at like, can you do something better?
For random.
For random errors, it's like if you compare BP for the classical case, it would beat the thresholds you get by large factors. So people have looked a little bit at whether you can do better than that with some of the arguments. But I don't know anybody's been able to like separate it from clusters like this. It seems like if you can't do it classically, it would be harder to do it.
But there exist already these quantum arguments by Causier, Verrier, which I guess we just borrow the quantum arguments.
Yeah, so maybe they apply it classically as well.
Maybe. I guess I'd be happy to.
Yeah, I think it's also a different situation because in the hypergraph product, you have these like 2D, right? Where your distance is only 1D, but your space is 2D, which is how you get the square distance. And you don't have this in the classical setting. So it's maybe this argument would not, like maybe argument for D, which is square root n, would not hold for D, which is linear in n, I don't know.
Because in the classical case, there are arguments that work really better. Like your first round, you can
Practically get everything. Yeah.
with random arguments, and random arguments tell you that immediately after the first round, you fall below the determinant bound. So yeah, these types of arguments that work very well in the classical case,
They don't work here.
The quantum case, straightforward.
Yeah, question if it's difficult to analyze on general LDPC codes, perhaps you could do it for like 3-dimensional hypergraph product codes or high-dimensional, because they have kind of local structure. Like that, will it be easier to analyze? I mean, I know you haven't thought about this, so this is what that would be.
Easier, yeah, I mean, I don't know.
In terms of being able to think about random errors?
Well, in terms of being analyzed, construct the algorithm for specific codes.
I see.
Right. Because I understand correctly that you only know how to work it with hypergraph product codes, but not for generic
For that small set flip, this Causier paper provides all the statements for threshold theory. Right?
Can you repeat the question? I did.
You're discussing the decoding radius.
Yeah.
But for small set flip, the previous work shows a stronger statement for proving threshold theorem.
For random errors.
For basically local stochastic error.
Yeah. This is only for like adversarial type error, not for random.
Do you expect that this argument in the previous work may generalize to this algorithm, or there's some difficulty?
So I think this is what Ani already answered, that the argument that the errors are like in disjoint clusters, like the errors would still be in disjoint cluster, but then the question is how much, like because L is larger than E, maybe the errors are disjoint, but if we try to grow the L, they might intersect. We don't know. This is like the challenge in handling stochastic errors.
Can you give us an intuition for why your algorithm requires a super linear time?
Why the Eurasian conversion algorithm is not straightforward? So, okay, so in the classical setting, it's sort of very easy because once you know what is not an error, then you can sort of just get the right value of all the party checks and you directly get it. In the quantum setting, because you don't really have, like you have cosets, then you need to, basically the algorithm solves a Gaussian elimination. Like, and we don't have something which is better than to solve Gaussian elimination.
There are no more questions. Let's thank Inbal again.